Okay, well, hello everyone. This is Calculus Fall 2020. My name is Scott Grizzard from the University of South Florida. And today we're doing the quiz review for, which quiz is this? 12A. As usual, there is chat in Twitch. There is chat in Blackboard Collaborate Ultra. There are polls in Blackboard Collaborate Ultra. Let's get started. So, the idea here, and I apologize for any artifacts here. I tried to make the green screen has a shadow that I can't seem to get rid of. Nothing's perfect, I guess. Well, it could be, but then I'd be spending a lot more money than I already am. So here was the idea. A farmer wants to build a rectangular plot, right? Adjacent to the north wall of his barn. Now, he doesn't need any fencing along the barn, right? So this side is free. And the west side here is shared with a neighbor who's going to split the cost of the fence. You know, they're good neighbors. He couldn't make Canada pay for the whole wall, but he's going to split the cost of the wall with Canada over there. So that's $10 a foot. All right, so he's going to split the cost for that. And there's this large oak tree out here. That means that this side of the fence cannot be longer than 180 feet. Okay? Sort of a limitation here. Okay. And fencing costs $20 per linear foot to install. And the farmer wants to spend $6,000. What is the configuration? Find the dimensions and what's the biggest area. So what's the biggest area he can enclose for that $6,000? And what are the dimensions of the thing? Okay, so how do we feel 1 to 5 about kind of what's being asked? Kind of the setup. Getting from the words to the picture. Okay. So what I'm going to do here, what am I trying to produce? I'm trying to produce area. So production is that area equals length times width. And my cost is going to be not letting me move again. Okay, there we go. And my cost is these things here. So it's going to be $10 for whatever this side is, $20 for that side, and $20 for that side, and this side is free. So I've got 10L plus 20W plus 20L. And this right here is plus 0W. Right? That side is free. And that equals 6,000. So I'll just put C here. So this is fixed. And this is optimized. Okay, so 1 to 5, how do we feel about those two equations? That those are the two equations. Right, so I've identified what I'm trying to produce, its area, and I've identified my cost function. In this case, actual money is involved. you know, I don't have some fixed amount of I have a fixed amount of money to go to the store and buy stuff, right? I don't have the ones we were working with before. I was kind of like, this is this, you know. Um, the cost was not necessarily in terms of money. It was like in terms of building material. But here we've got money. Okay. So what I'm going to do is I'm going to combine these two functions. So I've got the simplified version of this is going to be 30L plus 20W equals 6,000. And what I'm going to do is I'm going to lose I'm going to divide through by 10 here and get rid of the just to make the numbers a little bit smaller because I can. And I'm going to solve for one of these. And in this case, there's actually a reason to pick L to be the one that we want to move. The reason why we want to pick L, we could pick W and it'll work, but L has this weird condition on it. So what I'm going to do is I'm going to solve for W so that I sub back into L. Now, you don't have to do that, but, you know, I'm going to have to check to make sure that my optimum obeys these things, right? So my problem now is I want to solve this here. So I'm going to toss that in there and I get A. So this right here gives me 2W equals 600 minus 3L. So this is going to give me W equals 600 minus 3L over 2. Which is the same thing as 300 minus 3 halves L. Okay, so that's my W formula. And then I'm going to sub that in here. So A equals L times this thing, 300 minus 3 halves L. And since I'm about to take a derivative, I'm just going to go ahead and multiply this out. And I get 300 L minus 3 halves L squared. All right. So what I want to do is I want to maximize A of L on 0, 180. Okay, so how do we feel kind of about that finding one equation now? Okay, so I've got dA over dL equals 300 minus 3L, right? The square, the 2's cancel, and I get this equation. And I'm going to set it equal to 0. So I'm going to wind up with 300 equals 3L. Right, which it gives me that I divide both sides by 3 and I get 100 equals L. And note, 100 is in this equation. Okay. All right. I want this to kind of be lower. When I did this earlier, it like deleted all my little note things. It was really annoying to me. Okay. So now what I need to do is I need to check to see that I have a max. Okay. Well, I can do it like this. There's two things I could do. I could do two things. I could actually do three things. Okay, so I need to check these things. So I could do one of three things here. I could just sub in the endpoints and see that both endpoints are going to be less in my original function. I could do a first derivative test, right, which is to take L to be 99, or I'll choose something else. I'll choose 50 and 150 or something like that, and then throw that into the derivative. Or I could take a second derivative and note the direction, okay? So I need to do something here to talk about check min or check max. Okay, so let's see. I'll write that right here. Check min, check to see if that is the max. Okay. So 1 to 5, how do we feel about the fact that I need to do this now? Somehow I need to make some argument to see whether or not I have a max. So where'd my thing go? That's not it. That's not it. That's it. Okay, so 1 to 5, how do we feel about taking the derivative and setting it equal to 0, finding that critical value? L equals 100. Okay, so let's ask real fast about that first, because I didn't ask about that. So take the derivative, set it equal to 0. That will give me that L equals 100. So I solve for my critical values. Okay. Now I could do one of three things. I could check this, right? I could just do, well, what's A of 100? And note, I'm going to have to make that computation anyway. So let's just, start doing that. I picked option 1. Since I'm going to have to kind of make that computation anyway, let's see. A of 100 equals, okay. So I come back up here to where I had my equation, and it equals 300. Is it going to be easier to do 300 minus that? Yeah, this is going to be. So it's going to equal 100 times 300 minus 3 halves times 100. Okay, which equals what? Well, let's see. I can do 3 halves, so this is going to be a 50. This is going to be 50 times 3. This is going to be 150, so it's going to be 100 times 150, which equals, let's see, I need 1, 2, 3 zeros, 1, 5 with 1, 2, 3 zeros. Okay? Let's see. A of 0 equals 0. Should it be... No, I'm using this equation right here. But yes, you could do that. I didn't want to deal with 100 squared. I could have, if I felt like it, but I didn't feel like it. It would have given you the exact same answer. A of 0 equals 0, and A of 180 would equal 180 times 300 minus 3 halves times 180. All right, now 3 halves times 180 is going to equal what? So this is going to be a 90. So this is going to be 3 times 90. I already don't like this problem. Where's my calculator? 180 times 300 minus 3 times 90. And that's going to give me 5,400. Okay. Someone hopefully said that. Okay. So that, therefore, A of 100 is the largest. This is in the way. Okay. So 1 to 5, how do we feel about that? Making that argument. 1 to 5 here. I put it back into the, just like I was doing one of those problems from before. Checking endpoints. Checking crit value and endpoints. So 1 to 5, how do we feel about that thought? I got a closed interval. I can just make an endpoint argument and be done with it. Okay. Now, for this one, I probably would have, the fastest way is probably the second derivative test on this one. So if I did option 3, it would look like this. Right? I had dA over dL equaled 300 minus 3L. So that means d squared A over dL squared equals -3, which is less than 0. Right? So I have a max. Right? That's the fastest way to do this one, is just to do the second derivative test. But, I kind of wanted to show that it was the exact same problem as the ones that we were doing where we were just maximizing on a closed interval. Because that's what the problem is. You're maximizing, you've got this setup bit here. But once you do this, your problem's been reduced to maximizing this equation on a closed interval. Okay? That's kind of what I wanted to show, that they're the exact same problem. Okay. Now I'm just going to solve for W. Well, I already solved for A. So A equals 1,500 square feet. W equals where was my W? 300. Oops. I just did something that it didn't like. Okay. 300 minus 3 halves of 100, which equals let's see, 3 halves, that's going to be 50, that's going to be 150, that's going to be 150. So, the optimal arrangement is L equals 100 feet, W equals 150 feet for an area of 54, well, nope, not there, 1,500 square feet. Okay, so 1 to 5, how do we feel about that, where I just the kind of summarizing everything? Okay. And now what I'm going to do is I'm going to go back quickly and I'm going to check to make sure I answered the question. Okay. So I'm going to zoom out here and I'm going to check to make sure I answered. Find the dimensions for the plot and state the area enclosed. The optimal arrangement is that. There's the dimension for an area of that. All right, so I just make sure I answered all the parts of the question and that I have my units and everything. Okay. All right. So, are there any questions about those? That's a kind of typical style optimization problem, right? I've got some, and it does, sometimes you'll have one of these, sometimes you won't. You did in pure leading, your problems didn't have these kind of constraints on them. Here I did. I just had this. There's a tree there. It can't be bigger than the tree. But sometimes they'll matter. Here they didn't. Right? The fact that this gets nowhere near the oak tree. Okay. This is the way, by the way, that these types of things usually get created, okay? Graded. So you've got like a point for, you get this, you solve it, you substitute, you take the derivative, you find one of the things, you sub back in, you find the other side, you check the endpoints, you do a first derivative check, and then you do something to state that you know that you have the answer. Okay. All right. There is another way to do this, by the way. And this is in your book, and I'm going to be talking about this tonight. But this is kind of a preview. I could do this another way. So you notice here how I took the derivative when I set it equal to 0. What would have been the derivative of this cost function? What would have been the cost is fixed. So it would have been 0 as well. So I could, if I wanted to, and I'm going to talk about this tonight, but this is just a little preview. I could take the derivative of A with respect to L implicitly, and take the derivative of C with respect to L implicitly. Now, this one would have been set to 0 because area is the thing I want to optimize. This one would have been set to 0 because cost is constant. And I could wind up solving for dW over dL in both. And then I just plug it in here, and I wind up with this equation here. And then I would have just solved for everything. So there is another way to do this. Okay? So I could solve for this ideal ratio. We'll talk about that more today in the problem set. In the problem set, we'll be solving for the expansion path, and then in the lecture, tonight, I'll be showing you how to do that. It's kind of a nice little trick. All right. The true false. If f prime of u equals 0, then f has a local min or a max. That's false. Why? No, false.
No.
Big no button. I need a big false button, right? Okay. The reason why is that it is true that if f has a local min or a local max, then f prime of u equals 0. But the converse is the opposite is not true, correct? Because I could have a function like x cubed where I don't have a min or a max here. Okay. So 1 to 5, how do we feel about that? Okay. If f prime of u equals 0 and f double prime of u is less than 0, then f has a local max at u. So that's the second derivative test. I draw a little thing here, right? I got max. This is concave down. That's true. Okay. 1 to 5. How do we feel there about 2b? Okay. For 2c, if f prime of x is greater than 0, then f is decreasing on that interval. Right? Nope. F prime of x greater than 0 looks like that. F is increasing. Right? So,
No!
false. Okay. 1 to 5, how do we feel about that one? Okay. If f has a critical value at u, then f prime of u equals 0, or f prime of u does not exist. That's true. Definition of critical value. Okay, how do we feel about that? 1 to 5. Okay. If f and g are constant, if f prime of g of x equals g prime of x for every x, then there exists some constant c so that for every x, g of x equals f of x plus c. In other words, the functions are vertical shifts of each other. Now, 1 to 5, how do we feel about this? Okay, so polling 2e. That was one of those consequences of the mean value theorem. Okay. All right, so that's it for the quiz review. Let's get started on the problem set here. So let's end the stream.